Okay, so the heart of this particular assignment is subtyping. So in particular, the important rule is this rule called subsumption, which says that given an expression E which has type T prime in the typing context G, if T prime is a subtype of T, then you can consider E to be of type T, right? What does this mean? So let's look at an example. So here is just recalling the ideas, right? So subtyping, we write that as T1 subtype of T2, read as T1 subtype of T2. Given an expression E with type T1, which is what we mean here, right? Type T1. And if you know that T1 is a subtype of T2, you can consider E to have type T2. What's an example? So here is the hierarchy that we had seen earlier, right? Animal, feline, canine, cat, tiger, and so on. So here's a function. So all the felines have retractable clause, right? So maybe I'm defining a function called retract clause, which takes a feline object as a argument and then retracts a clause. So it doesn't return anything. So what does this accept? It accepts any feline objects, but it also accepts any objects that are subtypes of the feline object. The subtypes here are the cat and tiger. Right? So we know that cat is a feline, so tiger is a feline as well. So it should have a retractable clause. But how do you make sense of this one? Let's say I have a particular cat called Henry, right? Who is a cat. So this one is a object, right? Or you can think of this as a value in our context. So now this has type cat, right? But this particular function, retract law, expects a feline. But luckily our subsumption rule says that if you have a expression E, this value that is Henry has type T1, right? Has type cat. And if T1 is a subtype of T2, we know that cat is a subtype of feline, then you can consider E to have type T2. So you can consider that Henry has type feline as well. And now you can apply retract law over Henry, right? So that's the idea of subtyping. So let's look at the details now. So this is so we saw this in the context of an object-oriented hierarchy, but here we have tuple types. So what are the different possibilities? So the subtyping relation itself is defined here much earlier. So let's look at the simplest one, right? So if you have an empty tuple type, then it's a subtype of itself. So wherever an empty tuple type is expected, you can pass an empty tuple type, right? So it's its own subtype. And the second one we have is given a tuple cons expression T1, T2, you can say that that is a subtype of T1 prime, T2 prime. If independently, T1 is a subtype of T1 prime and T2 is a subtype of T2 prime. So this is known as depth subtyping. An example here is cat, tiger is a subtype of animal, feline, right? So I mean, this doesn't perfectly fit the types here because this has to be a tuple type. But let's forget the details for now. Let's just say that given a pair where you expect an animal and a feline, you can always pass a cat and a tiger because you can sort of imagine using the subsumption rule but this particular whatever expression that satisfies this type satisfies this type as well. Okay, so that's depth subtyping. So depth subtyping is captured in this rule, right? So width subtyping is quite interesting. So it basically says if you have more information right? If you have more information here, then you can always use it in a context where you expect less information, right? But this formulation itself is quite odd, and this is what is captured here, right? So if you have a const t1, t2, then if you have a nil, then that's certainly a subtype. Um, okay, so how does this make sense? So let's look at an example. Okay, so the example is here. So consider this particular expression, right? So I have a function f which takes a tuple type as an argument, right? Extracts the zeroth element from the tuple and then applies that to an empty tuple type. So what is the type that you can give? So we know this particular thing has to be a function type, right? Because it is on the left hand side of an application. So that is going to be a function type, and we are also extracting the first element of this tuple. So T has to be a tuple type. So the type that I can give this particular expression is it's a tuple. And the first one is a function type that goes from um, nil to nil, right? And then the second one is an empty tuple type. We don't care about this because we are only extracting this one, right? Zeroth one. And what it returns is when you apply an empty tuple expression to this function, which has this type, it has to return the empty tuple expression. So which is what it returns, right? So I can certainly apply f to a function like this, which has a tuple which is of length 1, right? It has one particular element, and this is an identity function, so this has this type. But observe that we only care about the zeroth element here. Even if this tuple were longer, it is okay to pass. It is okay to apply this function on that longer tuple because we don't care what the rest of the arguments are, right? We only care about the zeroth argument. So here is an example. So I am applying this function on this tuple, which has two identity functions, right? And the observation here is I should be able to apply this successfully because I am only extracting the zeroth element. This is the first element. I don't care. It could be anything, right? So, but how do we say that this particular expression is well typed, right? And that is where the bit subtyping comes in handy. So, what is the type of this particular expression? The type of that expression is first has to be this identity function, right? So this is null to null, so which matches this one. The second one, I just give null to null. It could be anything, right? I say it is null to null. And then the last one is a null tuple null expression. So this is tuple null. I want to consider this to be a subtype of this one, right? This is what I want because this is the function argument that we have here, all the way here, right? This matches this one. So whatever the type of this, like this type should be a subtype of this one. This is enabled through with subtyping, right? So here let's have a look. So here we see that the type here we need to show that it's a subtype of this particular type. So how do we do this? First we apply depth subtyping, which subtypes on each component, right? So I need to show that this type is a subtype of this one. So I have that rule here. So we will discharge it through function subtyping. We haven't seen function subtyping yet. We'll save it for the rest. But for now, you can consider that this is the same function, the same type. So it has to be the subtype of itself, right? And for the other side, the right-hand side, the type that we have here is this one, which matches this. And the type that we have here is a tuple nil type, right? And this is directly discharged through with subtyping. So which is what is given here, right? Which is what is also captured here. Okay, so that was depth and width subtyping. So there is one more curious thing, which is function subtyping. So the thing with function subtyping is it looks wrong on first view, right? So um, here is the um, version of it written down using Greek letters essentially. So what do we have here? So we have a function that goes from tau1 to tau2. I want to say that that's a subtype of tau1 prime, tau2 prime. So this sounds fine. So I need to show that tau2 is a subtype of tau2 prime. But here observe that the arguments are sort of reversed order, right? So I need to, it says, the rule says that I need to show that tau1 prime is a subtype of tau1. And that looks quite odd. And it turns out that's the right meaning, the right semantics that we want. So why is that? Let's take a look at another example. So here is some higher order retract law, right? So earlier we had defined retract law. Here we are going to define retract law 2, which takes a function feline to feline, and then it's going to return unit. What is it going to do? It is going to apply this function, the higher order argument, on some particular tiger, tiger1, right? And it's going to get a feline back. We certainly know that tiger is a feline, right? And it's going to get a feline back. And once you get a feline, you know that you can apply retract law on it because every feline can retract its claw. So that matches its type, right? And assume that every animal also has a name that is accessed with dot name accessor, right? This is just for convenience. So now consider that we have this odd function, right? Which given an animal, it returns a cat with the same name as the animal. So how do I do that? So the function is called make cat with name of animal, and it's going to return a cat, right? And it is going to make a new cat, right? C, and it's going to say, oh, the name of this cat is the name of the animal. I should also do C dot. I should also return C here, right? Okay, that's the function. So now the question is, let me move it a little bit. Now the question is, can I apply retract clause to this function on make cat with name of, right? On make cat with, oops, on make cat with name of. Can I apply this? Observe that the expected function type is feline to feline, but this one is animal to cat, right? This is okay. It should be okay. Why? Look at this. So I'm going to apply retract clause 2 and make cat with name of. So if you just expand the definition, the body here, oops, and that is going to be retract clause of, you're going to apply the higher order function, make cat with name of this tiger. You're going to get the name of this tiger, and you're going to return a new cat, right? And you can retract the clause of the cat. So by beta reduction, this works well, right? So it shouldn't get stuck. This particular expression shouldn't get stuck. But observe that we have a curious thing, right? So it's feline to feline, but on the argument side, we go up the hierarchy. From feline, we go to animal, and for the result, we go down the hierarchy. From feline, we go to cat. So this is precisely what is captured here. For the argument type, we go up the hierarchy, and then for the result type, we go down the hierarchy. So how is this possible? So if you directly apply the rule, I want to show that animal. So a function that takes an animal returns a cat is a subtype of function that takes a feline returns a feline. So we have to reverse the order for the argument type, right? And that type is feline. We have to show that feline is a subtype of animal. and that cat is a subtype of feline. Both are true, right? Our hierarchy defines both to be true. And the intuition here really is that um, you can sort of, the expectation is that you supply a function of this type, right? And you can always give it a function which expects less, right? And then offers more. By expect less, I mean, so the original function type is feline, but you are passing it a function that only expects an animal, right? So this is expecting less than what is actually provided by the context, right? And it offers more. So the context expects the result of the function to be feline. You're actually offering a cat, and certainly cat has all the features of a feline. And that's the intuition behind why the arguments are the subtyping rule for the function argument appears reversed. But that's the right semantics that we want. And this is what is captured here, right? And now that we've worked out all of the types, I think it is up to you to show that this particular encoding actually um, preserves type soundness, right? So I will stop here.